Good evening. So we have been discussing partial differential equations, and we got through heat equation, wave equation in one dimension, and then in two dimensions Cartesian coordinates. At this point, I want to show some of the projects from the previous time I taught this course, so that you can see how the rest of the discussion on cylindrical and spherical polar equation will actually help you select a problem and execute it. So when I say problem, I've been kind of keeping it vague about what exactly is my expectation and what are you supposed to do. So let's spend some time today talking about it. Okay, so along the way, feel free to ask questions. I want you to actually, this is the, I would say, the capstone part of the course, in my opinion, where you have learned about differential equations so far, and I want you to select a problem and apply it successfully. Okay? So we'll start with a few projects that were good, in my opinion. So this is a problem which was done by a student who actually got her master's in physics, and she happened to be my PhD student as well. And she took upon solving the Schrodinger equation in a 2D circular domain with the help of Bessel's equation. So how to set up the main physics, from that reduce it to a problem that is like a Bessel's equation, and then obtaining solutions. The first part will change. You may not be into physics, you might be into structures or fluids or heat transfer, whatever. But how do you set up the problem? How do you get results? And then how do you analyze or present it is what I want you to take away from this. And these slides were from her class presentation, which was about 10 minutes per student. So same thing that I planned for this class as well. So, oops. So the slides had like a outline slide, and she explained what is the motivation to select that particular problem. This is again something subjective, but you are going to use your own interest. Like, this is the place you want to show your interest and what you want to execute as a project. Okay. Problem statement in mathematical terms. So the previous slide was more about qualitatively explaining what is being done, and then writing it as a mathematical statement, saying defining the potential, and essentially to solve the Schrodinger's equation in a circular domain. That is, as a function of r and p is the chosen problem. Okay, and find out the wave function. That is, the goals of the calculation were to calculate the wave function and the probability density, which is the amplitude of the wave function, psi squared. The theory starts with stating what physical law that you will be solving. You are not expected to derive this or anything. It could be some equation that you get from another paper or textbook or whatever. So start with the PDE that defines your problem. And then you want to clearly express the solution process as well as the boundary conditions. So in this slide, the boundary conditions aren't there, but we start with this equation which contains a Laplacian operator and a potential energy operator. The potential is where the physics comes in, and that was defined in the previous slide. So set up the equation using separation of variables. It was reduced in two equations, one equation in terms of the radius and other equation in terms of, I think the other equation would be, an exponential type solution. So once you set up the Bessel's equation, you want to write that in terms of Bessel functions with boundary conditions, and then get the form of the solution which you will finally start to analyze. So this part is up to here. You would reduce it to a form that is recognizable to you based on the equations we are learning now and the equations we learned in module 2 for ODEs. Once you get here, assuming you do your first project well, you would have learned how to solve a ODE. You would be able to get the solution, and the expectation on the second project is for me to see how well you can take a solution which depends on a parameter vary that parameter to generate different modes or different possible basis functions and to visualize that solution. Okay, so here is the value of nu being varied. I mean, just to illustrate for us, what is the 0th order Bessel functions, first order, I mean, nu equals 0, 1, 1 and 3 and so forth, and her code to calculate that, which is really the code that I am asking you to develop as part of project 1. Okay? I think in this maybe she might have used built-in functions, or no, she has this one line up here, line 21, where she develops the Bessel function value. This is what I'm asking you to write for project 1 to get that practice. Okay? And here is the results for wave functions. The wave function depends on two parameters, nu and n, which can be independently varied. So for each combination, you will get a different function that can serve as a basis function. And in physics, there is a specific interpretation to the probability density, which is psi squared. So you would compute psi multiplied with itself, and for each combination of nu and n, here is the probability density, which, if you know quantum mechanics, is where the electron is likely to be found with this probability. So you'd want to give simple physical interpretation of whatever problem that you are solving as part of your presentation. So she had more results for higher modes, like higher values of nu and n, and some conclusions based on the analysis. Yeah. So yeah, one of the challenges listed is obviously understanding the meaning of the results. Something we always struggle with, right? All right, so that was one more physics heavy. Maybe if I can find something that is more heat transfer or mechanical engineering related. So this was by another student, Ken Mitchell, who was, I think I remember, a master student with Dr. Marchetta. So his interest was in heat transfer. So again, he started by discussing what is this Grates number and how is it related to heat exchanger design. Set up the problem, that is, give in your 10 minutes, at least 2 minutes you should spend motivating what you're trying to do to take the listener along. Okay. Here is the classical problem with the assumptions that go in with the modeling. The equation that describes the temperature evolution as a function of space, in this case z and r. And before he solved it, he actually non-dimensionalized them to get a more compact equation with boundary conditions and initial condition. So this, you can see, is obviously an equation that is of the form 1 minus x squared times a derivative plus something times the function. So with this transformation, he was able to get a ODE and then solve that ODE for different values of n, and finally obtain the temperature or dimensionless temperature of this form. Here you can see here that the function phi n times psi, sorry, phi n is the function that serves as the basis function or the orthogonal function. Okay. This was actually a very nice presentation that I recall, because that student also explained how he got the solution process or his way of implementing it, which was actually educational to others. And then calculating the coefficients that appear in the solutions, finally plotting the results and explaining it to the audience. I mean, if you get about 10 minutes, so you have to plan how well you can explain it within that short time. Okay? So it requires some serious rehearsal, and for you to plan your time, you just walked in there and saw some results and you don't give a deep interpretation of it, it would be difficult for the audience. Okay? And you could pick out theories from the literature which you can compare with, like he has done here, slug flow versus parabolic flow. I mean, this is essentially what, like saying, in the equations that he solved, there is a parameter called Vz, which is the maximum axial velocity. This, if you assume a slug flow model, is constant across the cross section, whereas if you assumed a parabolic flow, this is maximum at the axis. So there is a small difference in the solution depending on what you assume. Okay? And some conclusions based on the presented calculations. Any questions so far before I show you another example? Let me see if I can remember this project. So this is another heat transfer problem. Yeah. Maybe I'll pick something else. All right. Okay, but this was a nonlinear solution. Let's see here. So this was another, a lot of people I think chose heat transfer. So this is again, structure is almost same in every presentation: motivation, problem statement, theory, solution methods, and then results and discussion. Describe the geometry, try to exactly communicate that, set up the equations. In this case, the student is trying to derive how the boundary conditions are obtained by doing, I mean constant temperature at one of the walls and zero here, sorry, RF is outer wall. Okay, so this is like a no flux boundary condition or insulation boundary condition at R equal to RF. Go through the derivations. So at the end of the derivations, he is coming up with a set of equations, like a second order equation that he's going to solve. And here is the equation, and the general solution is obtained as the sum of the Bessel functions. And then he is setting up the code to solve the Bessel functions, which is similar to what you're doing in project 1. So overall, I would say that project 1 is sort of like getting you half of project 2. Project 2, in addition to being able to solve ODE or a PDE, also requires you to think about selecting a problem, coming up with the right motivation, taking a physically relevant set of boundary conditions, converting them into math, getting a solution, and then obtaining solutions, and then doing some analysis or discussion on them. Okay, so I've left a lot of things that I don't really go over in this course, like for example, selecting a problem or doing analysis or discussing your solution. All these you're supposed to do or think on your own. Okay, to help you prepare your problem or prepare your thinking, I try to post like a grading criterion. So here is the rubric that I used last time. I could make some changes to this, but it worked out pretty well as well. So if you see here, there is like a scale that I have given. Remember, this is only like 10 minutes that you are going to present. So I don't think I can get more granular than this. Like giving you in fractions of 0.1, I don't think is possible. So it's like needs work. Needs work could also be bad. good, very good, and great. So this is sort of the scale that I've come up with. The categories are, broadly speaking, slides and visuals. If you put enough time into making or organizing your content properly, conceptual knowledge so that you kind of exhibit the understanding of the problem that you're trying to solve. You're a clear presenter who talks clearly and pace yourself correctly. And technical presentation, not only that you are a good speaker, but is the content on your slides correct with units, the analysis makes sense, it is well explained, the conclusions are meaningful and based on data. These are the kind of things I look for under this. Typically what I do is I do my own evaluation. I also distribute these sheets to everyone in the class so that you can also evaluate your peers, and I try to understand what I think and what you think about a given presentation. So if you are presenting, you will be assessed by me and everyone else. That applies to everyone. So I could understand how it came across to me and how it came across to the other students. Okay. For those who are not very clear about how to organize your slides, or you don't do that as often, I've posted these template slides, which I'm not like insisting that you should use. You can always make your own template and or your own style of presenting. I strongly encourage that. But for those who don't have like or not who want some help, here's a template. Use a title slide, some of my tips on what exactly you want to put on there. Especially, I try to emphasize a lot more on using pictures than words. Try to put more, more graphics than text on your slides, generally speaking. Outline slide. I mean, if you are doing a research talk, I generally don't emphasize this, but in a short course, probably help you organize. Again, some tips on that. Keep it logical, keep it brief, make it a nicely or interesting story, entertaining story. Motivation, problem statement. I mean, you can see that I gave this template last time and most presentations ended up looking like this. It's also okay to have your own style. I actually like that. I don't want people to depend on this as much as possible. Okay. Any questions? So I put these under the folder project 2 materials for you to look at. Okay. I'm not posting those slides of prior year student presentations, mainly because I don't know if those students will be okay with it. I didn't get permission, but this recording will be posted. All right. Are there any questions? Have you started thinking about your project at all? Maybe you're still working on the first project. But I wanted to get this information out early, so you would see this is coming. This is like one evening, 10 minutes is going to pretty much determine 20% of your grade. So you can see how non-linear that 10 minutes is going to be in your course, timeline. So please prepare well. Want all of you to succeed. I'm not looking to punish you. I don't have some mystical high standards that nobody should meet. I want all of you to be good presenters. Okay, so please work hard on that. With that said, let's move into so last lecture I did solving the Laplace equation in Cartesian form on a rectangular domain, basically this equation. So one place where I kind of diverged from the book is In the book, the derivation is done for a rectangular domain where one of the dimensions is A and the other dimension is B. Whereas I went in with both sides being equal to A, and although we didn't make any mistakes, like if you take the formula from the book and substitute A equal to B equal to L, we would still end up with the formula that I ended up deriving. But it wasn't satisfying to me because I made a lot of mistakes on the way, and I didn't like that. I didn't like the way I did it. Okay, I wanted to redo that, but instead of going over it again in one lecture, I would like to postpone this slightly, maybe to the next lecture, and start on the next topic so that we can revisit this with fresh eyes. I do apologize. I did made a few slip-ups, but hopefully today it won't be there. Okay. So with that said, if you recall, we have seen 3 equations so far. This we have sort of seen, but we want to re-see it. We also saw the wave equation in one dimension and the heat equation in one dimensions. As an extension, if you combine this solution process with any of these two, you could also get the wave equation in 2 dimensions and the heat equation in 2 dimensions. We are not going to do that, it's pretty laborious, so we'll skip that. But in the future, if you need it, you know how to do. Okay, it starts with always the same idea that u of x comma y comma t is a function that is of a function of x and y, and then a function of t, which then splits into, let's say, h of x and q of y. So eventually you want to get a solution in terms of x, y, and t. The procedure is always the same. You just have to be methodical and careful to make it consistent with the given boundary conditions. Okay. So this problem, I hope to revisit next lecture and do it properly without mistakes. Okay. So that said, let's jump into the next type of domain or coordinate system. So we have seen Cartesian. We now want to see what is known as cylindrical or polar coordinates. So cylindrical or polar coordinates can be 2 ways. In general, you have r, theta, and z. So if you have a circle, you know all of this, I'm just recapping. So here is the origin, and if you have any point P, if we denote P with coordinates r and theta, okay, if we are interested in a function that is a function of r and theta, we usually call it circular or cylindrical, polar, or just polar. Okay, that is usually problems that are infinite along the axial direction. That is, assume some kind of a cylinder that is coming out of the plane of the board, and that cylinder extends, or that cylindrical domain extends in the axial direction to infinite length. If most of your process is confined, so for example, you have a very long cylinder and you are interested in a process that is confined to a very small region where delta is much lesser than z, we ignore the changes that happen along the z direction to just say that we ignore the dependence of u on z and assume that u is a function of r and theta only. So this is one of the most common ways to deal with infinite domains along the axial direction or along one length or one spatial direction. The other approach, or the other way cylindrical coordinates is often used, is to say your function u is a function of r and z only without any dependence on theta, which is also commonly given the name axisymmetry. That is, it is symmetric about this angle theta, so we say that partial u over partial theta is approximately 0, that is every angular direction is the same, and so u is only a function of r and z. Can you give me some examples of situations which are axisymmetric? Me, any engineering or physical context in which you can think that the variable that you are trying to track does not depend on the theta angle. So any axisymmetric physical process. Fluid flow, right? You want to say fluid flow, if you have like an example where you have a pressure gradient delta P, so you have P1 and P2 that is driving the flow, so there is an axial flow, your walls are fixed, so there is no motion at the wall, so you write boundary conditions like V, Z at R equal to R is 0, and at the center you have some kind of a boundary condition which is based on symmetry, and Vz does not depend on theta. What does it mean to say that? Literally, what does it mean to say something doesn't depend on theta? How will you verify it if you are in the lab and you have a velocity, a fluid velocity sensor like a hardware anemometer? How would you literally verify this statement? How would you verify anything is axisymmetric or anything doesn't depend on theta?
We measure it in two different angles and it is.
And if the value doesn't change or its value is nominally same, so for example, if you measure it, say from theta equals 0 to theta equals nearly 2 pi, and you get for all values of theta nearly the same value of the quantity, what does it mean geometrically? It means du over d theta doesn't vary, or u doesn't vary depending on theta. So on the modeling side, it's always easy to make these assumptions. An assumption will usually simplify your mathematics, but as an engineer or as an applied physicist, what you want to do is make sure your assumptions are grounded on some kind of reality check / measurements. Since I like doing measurements, I give my examples like this, okay? But always before you make assumptions, you need to have a justification. This is one of the things I'll be looking for in your project or your presentation, is that you don't be afraid to make simplifications, but be ready to state the rationale behind your simplification. Okay, that's all I'm looking for. So these are two ways in which we do cylindrical polar problems. So we want to be able to solve this, solve the equation that will allow you to calculate u as a function of either r and theta or r and z. So we'll start with the 2D wave equation in polar coordinates. one that's going to involve r and theta only. And that equation would be second derivative of u with respect to time is equal to c squared r squared we are not really telling you how this equation is actually set up. Where are you getting the second derivative? Why is this multiplied with 1 over r? Why are you multiplying this with the 1 over r squared factor? We're not going through that. This is something which we would typically cover under vector calculus, which is like the last module in our course. Sometime back, I used to have that as one of the third or fourth modules. But what ends up happening is, this is the topic, or PDE is the topic that I want to give most importance. It ends up getting pushed to the last and doesn't get the attention that I want to give. And then it also doesn't give you the time to do a project. So that's why I had to do this juxtaposing. But hopefully you will forgive me for that. The basis for how you get the Laplacian to be this expression will be explained in unit 6. Okay, so for now, just accept this PDE and let's think about how can we solve it. Okay. All right. So if we make the simplification, partial over theta is 0. That is, if we just consider the wave equation in the radial direction, let's start with this because it already has two independent coordinates, time and radius. So it's going to give us enough work to get started right there. And our domain, we'll write this r equal to 0, r equal to uppercase R, denoting the radius. You could have a domain that not necessarily represents a circle, but you could have a domain that is, say, r equals r1 and r equals to r2, such that it represents an annulus region or annular region, whereas this represents a complete circle. So at these boundary points, we want to write u so we want to write u at r comma t is equal to 0, meaning this is a fixed end. Okay. And depending on whether this represents a circle or this represents an annular region, the boundary condition on the interior point could vary. What's the difference between having a fixed end and having something, say for example, if this represents an entire circle, sorry, pardon my circle, but assuming that this is a circle, let's say this is like a circular plate and you are holding one end and you are perturbing this domain. That is, we are going to give this like an initial deflection and an initial velocity. How would you handle the center point? If you have a circular plate, you can put your finger on anywhere and try to depress the plate and give it an initial displacement or even give it an initial velocity. And you could super glue it to a surface so that the circumference is fixed, giving it a boundary condition of 0 value. What about the center point? If this plate is supported only along the circumference, What about the center? Is it supported? Should we assign it a boundary condition, or is it not supported? It is free to move. Or in other words, you are saying it should come out as part of your solution and not part of what you prescribe as a boundary condition. Is everybody okay with that?
I think the boundary condition right there is function u over function r is 0 because we would want continuity. Otherwise, like the shape of u, I'm not sure.
Are we okay with saying that the center should come out as part of the solution? Right? So imagine the other situation that you are not considering the entire circle, but say for example an annular disk. I'll redraw this here. So this is R1, this is R2, or this is R equal to 0 and this is R equal to R. So you can consider either the full circle or an annular region. Okay, the difference is when you do an annular region, you can have this end bonded or have this fixed, or in other words, assign a boundary condition to this end. You can do that always. If you are doing just the annular, you can also do the same here. Assign a boundary condition at this point. Right? But if it is a full circle, whatever solution that you obtain here should be the same regardless of whichever direction you approach it from. There has to be continuity at that center. Not only continuity, your solution has to be differentiable at the center. Or in one word, your solution has to be analytic at the center. And the way you ensure that is to say, if for example your solution is something, whatever the solution is, partial u or partial r must be 0 at r equal to 0, so that from every direction that you approach it, you would get the same derivative. So if you have a circular domain, and if it's a finite valued quantity, without not too much deliberation, the boundary condition at the center is always to preserve symmetries. If it's something else, this could also represent a heat transfer problem or any physical quantity. You could assign a flux or a constant value depending on your experimental apparatus or design or whatever. So annular can be different from the entire circle. That is my message, first message. Okay. So we are going to consider the circle, the annular, probably something you could try in a project or something. Okay. So let's write down our so at r equal to 0, we have partial u over partial r equal to 0. At r equal to r, let's say u equal to 0. These are our boundary conditions. And initial conditions, we'll say for 0 less than r, u of r comma t equal to 0 is f of r, partial u over partial t of r t equal to 0 is g of r. You remember your Bessel functions, right? So once we get to the Bessel's equation, you should be able to tell me what is the general solution, right? So we'll see how far we can get. So step 1, always to start, u of r comma t is a product of two functions which we'll write f of r and g of t. So book wants to use w of r. So I'll write g double dot times w equal to c squared times g times w double dash plus 1 over r w dash. So we'll write this g double dot over c squared g equal to 1 over w double prime plus 1 over r w prime, and we'll equate this to negative k squared. Which gives us g double dot plus c squared k squared times g equal to 0, and we are going to call this lambda squared, where lambda is c times k. And we'll write w double prime plus 1 over r w prime plus k squared w equal to 0. So here we want to clarify that this is second derivative with respect to r, this is first derivative with respect to r, and introduce a change of variables, introduce a new variable s which we'll define as k times r. So can we calculate dw over ds, which would be dw over dr multiplied by dr over ds by chain rule, which would be dw over dr times, what is dr over ds? 1 over k. So we'll write dw over dr is k times dw over ds. So recall what is r? R equal to 0 to r is your domain, which you have now scaled to s equal to 0 to k times r. So sort of like a scaled domain, scaled value of your domain in this new independent variable s. And similarly, you can get also what is the second derivative with respect to r, which would be k squared d squared w over ds squared. So what do we get? We have second derivative with respect to r plus 1 over r first derivative plus k squared w equal to 0. This would now transform as d squared w over ds squared plus k over, what is r? R is s over k. S over K dW over ds plus K squared W equal to 0. So you're going to have K squared, which we generally assume to be non-zero, which would give us d squared W over ds squared plus 1 over S dW over ds plus W equal to 0. Do we recognize this? Can you look up the generalized Bessel's equation? Can you please look up and relate with this? Which you can do by going to section 5.4 or 5.5. So Bessel's equation in general is x squared y double prime plus x y prime plus x squared minus mu squared times y equal to 0. Now do you recognize it? This equation is Bessel's equation with new parameter being 0. Right? If you set nu equal to 0, you will lose 1x and you're going to get double second derivative plus 1 over x first derivative plus y equal to 0. So you've arrived at the equation with new parameter being 0. So since you already took the first exam, what is the solution to this? C1 J0 of x plus C2 Y0 of x. Or since we have the equation written in terms of s, I'll write J0 of s and Y0 of s. So this would be W as a function of s. The project 1 which I've asked you to do typically is for problems in which nu is either an integer or the difference is an integer. So if you are going through project 1, this will not look very alien to you, I hope. Okay? So everybody is okay with this step? I could elaborate from how we go from here to here, but that's what module 2 was about. So we are not doing that again. Okay? So you have W of S equal to C1 C1 J naught of S plus C2 Y naught of S. S itself is not an original variable, it's only K times R. Okay. Still we don't know what K is. It has to be determined. Okay. But you do have boundary conditions. You do have this. How will you use it to figure out what is C1 and C2? So you can write this is R and this is S. When R is 0, S has to be 0. When r is uppercase R radius, this has to be k times r. Okay, so take the boundary condition u equal to 0 at r equal to r or s equal to kr. That is like writing u, which is w times g. If we assume g is not trivially 0, we can assume g is non-zero, which makes w 0 at s equal to kr. So w of kr, which is c1 times j naught of kr plus c2 times y naught of kr, and w of kr is 0. Okay. What do we know about this other function, the Bessel's function of second kind? It does involve j naught, but it is multiplied with a logarithm to make sure they are a non-linear combination. Okay. The other fact is y naught of 0 is actually infinity. You don't have to remember the full form of y naught to say this. You can assume that y naught, or you not assume. You can look up that y naught of x involves j naught of x multiplied by logarithm of x plus some terms. If you have logarithm of x, obviously when this x goes to 0, this function will blow up. Okay, so if you are working with a circular domain which starts at the center, this function is fundamentally incompatible with that, because it's going to blow up. And the only way you can make sure that this w remains bounded and finite is to choose C2 as 0, so that this problem is eliminated. So you have C2 being 0 to keep u to remain analytic. So we have used this information in a different way to select C2 to be equal to 0. If that is the case, you don't have to write this at all. All you have to write is C1 times J naught of KR is 0. Your WS itself, W of S itself is C1 times J naught of S, and remember you are going to later multiply W of X or W of R with G of T, which is going to come with its own two arbitrary constants. So you don't have to have a separate constant here. So we'll just drop the C1. We'll drop the C1 and write J naught of KR must be 0, which means what values of K will satisfy that constraint. What values of K when multiplied with R will lead to the Bessel function to be 0? That is the question. So just for example, when we write J naught of X equal to 0, have you tried visualizing this Bessel function? How many roots does this have? Sorry? Infinite. Because if you visualize the function, it is a decaying exponent that crosses the axis forever and oscillates about zero nearly. So depending on what interval you are interested in, you might have a certain number of roots contained in that interval. Is everybody okay with that? This is not a polynomial equation with a known number of roots. It has an infinite number of roots, and in our case, we are writing J naught of k times r equal to 0. Okay? So there can be multiple values of k which lead to this root or this function crossing the axis leading to a root. Okay? So treat k like a variable, treat k like a variable that takes real values, and k that treat a variable, a real variable, and list the zeros of J naught of kr. Before we go away from this, suppose your problem is not on a circular domain with a center at r equal to 0 and an end at r equal to r. Suppose you are interested in an annular domain with where r varies between r1 to r2. So r varying between r1 to r2, which means s will vary between kr1 to kr2. In that case, how will you proceed? Suppose, and I also give you boundary conditions, u at r1 is given to be, let's say, 0, and u, say, we'll just say it's u1, and u at r2 is u2. How will you proceed? Your general solution is w of s equal to c1 j naught of s plus c2 y naught of s.
Whether we can convert the function, our solution w of s in terms of u, or
So,
we
yeah,
can
sorry.
also convert the boundary conditions in terms of ws.
Well, you're going to also multiply this with g of t. Okay. One trick that you can obviously pull is to normalize this by, you can turn this with a scaling that reduces this to 0 and this to 1. By subtracting u1 from both the values and redefining, say, u as u minus u1 divided by u2, you could turn this into a 0 and 1. Okay, let's say this u1 is 0 and 1 for simplicity, but in general you know how to scale it. So you will have w at kr1 equal to c1 j naught kr1 plus c2 y naught kr1, and this w at kr1, let's say, is 0 equal to 1, w at kr2 equal to c1 j naught of kr2 plus c2 y naught of kr2. So c1 and c2 are constants which have to be solved simultaneously for a chosen value, or if you're targeting 0, you will have to plot using a computer, obviously, you'll have to combine J naught and Y naught in suitable combinations that add up to 0 and 1 simultaneously. So this becomes not only a nonlinear problem, this becomes not only a iterative problem, you will have to solve two simultaneous equations for C1 and C2 while trying to get them to add to 0 and 1. So you can see how incredibly complicated this can be, okay? But nevertheless doable. It's still all linear, so not impossible. Anyway, this was a sidebar to kind of help you deal with annular domains if you encounter them. Okay. Yeah.
Excuse me, if we solve for C1 and C2, what happens to K? Because right here we say KR is the roots of J0, and do we do the same thing?
Same thing, except you will have to redefine your problem statement as you have to pick out values of K for which the sum of J0 and Y0 will add up to 0 or 1. It becomes a little twisted. Here it's neat and straightforward. It's like asking what are values of K for which J0 alone will become 0. That is directly the roots of the Bessel's equation. So you'll have to basically add the two functions to see where they collectively go to 0, and it's like in phase and out of phase kind of thing. Okay. All right. So coming back to our problem, we are trying to figure out J0 of KR equal to 0. What values of K will lead to this? And this is like information that you could look up, because Bessel's zeros of a Bessel's function is something that has been tabulated in handbooks, or programs like MATLAB can readily give it to you. So you can go to MATLAB and invoke a Bessel's function and also get MATLAB to list its roots between a certain interval. So between 0 to 1 or 0 to 10, you can get all the roots of the function just by a subroutine. Okay. So values of K, will say Km of R equal to 0, where KMR are zeros of J0 of X. And Km happens to be, I'm repeating information from the book. So K1, M equals 1, 2, 3 and so on. K1 is equal to 2.4048. K2 equals 5.5201 and so on. You can write as many number of K values as you want, which falls between 0 and the value of R. Okay. So we write Kr equal to alpha m and K equal to Km equal to alpha m over R. So I should write these are all alpha values, alpha 1, alpha 2 and so on. And in a real problem or like a project that you're trying to do, R would not just be a symbol, it would take some value like 1 meter or half a centimeter, something like that. So your Km will end up having units of inverse length. Okay. So in general, Km is alpha m times R. Okay. Which would make W of S, which is W of KR, which is equal to Wm of alpha m over R times R. So the solution we are looking for is Wm alpha m over R times R is nothing but J0 of alpha m over R times R. Can I erase this middle part, the discussion around annular regions? All right, so you have W of R equal to J naught of, Wm of R is J naught of alpha m over R times R. This is one part of the solution that we have secured so far. The other part is G double dot plus lambda squared G equal to 0, where lambda is equal to Ck. Now K is no longer a mystery, so lambda m is C times Km or C times alpha m over R. So we'll write G double dot plus lambda m squared times G equal to 0. What is the general nature of this solution? It would be a cosine and a sine, right? So we'll write G of t is A subscript m cos lambda m times t plus B subscript m sine lambda m times t. So if we combine the solutions, um of r comma t is Wm of r times Gm of t. Which is J naught of alpha m over r times r multiplied by am cos lambda m times t plus bm sin lambda m times t. And m can take values 1, 2 and so on. We don't include m equal to 0, which corresponds to r equal to 0, because we already used that information as part of the boundary condition. So the entire solution u of r comma t is a linear combination from m equals 1 to infinity um of r comma t, which is like writing m equals 1 to infinity w of alpha m over r times r multiplied by, for just to keep it brief, gm of t. So this is summation 1 to infinity J naught of alpha m over r times r summation am cos lambda m t plus bm sin lambda m. This is u of r. Once you bring in the time component of the solution, this is the right place to use the initial conditions to get am and bm. So in the exam, you might be wondering, should I be doing all these steps in order to finally get a solution? In the exam, at least what I plan to do is start with a PDE, give you or ask you to do the steps to arrive at a set of two ODEs. And then I will provide either this step or I'll provide either this or this or this. And then ask you to use the initial conditions to get A and B. There could be a small variation in the boundary conditions. So I can give you the steps of setting up the two ODEs, but make a change in the boundary condition, which will force you to change the way this solution comes out. And then the rest of the steps is to get the entire solution. Okay. So the two ODEs that you are going to solve will be given to you. How you apply boundary conditions is the skill that I am testing for. Alright, so what exactly would you do here? So we can start with the first initial condition for u. F of r is nothing but u of r comma t equal to 0. This is like writing summation 1 to infinity j naught of alpha m r over r times am. Right? This looks familiar. This is our Fourier Bessel series, remember? That is, what is the generalized Fourier series? It is to write any function f of x in terms of orthogonal functions am, ym of x. That is the generalized Fourier series. Except in this case, ym happens to be j naught of this function, j naught of alpha m r over r. Okay. So one of the things you could have on your cheat sheet is, if this generalized Fourier series is needed, what is the formula for am? You could have that on your sheet. That would, once you see this, once you connect it with the generalized Fourier series, all you need to do is write down the value for am. So continuing here, am, what is our domain here? The value of r runs from 0 to uppercase R. That is our domain. So this is equal to 0 to r j naught of alpha m over r times r multiplied by f of r dr. The only difference here is, since this is a circular domain, we'll have to write this as r dr. Actually, technically speaking, it's 2 pi r dr divided by 0 to r j naught of alpha m over r times r squared 2 pi r dr. Can you kind of physically tell me why I did this 2 pi r dr factor?
along the periphery.
So our domain is like this. I mean, you know the answer, I'm just asking you to articulate it. R equal to 0, R equal to R. Okay. So when we are talking about an interval that is R and R plus dr, when you do this for a linear domain, this is just a length. When you do this in an axisymmetric domain, this is a length multiplied by this angle, which makes it an area. That angle is basically 2 pi. That is why we have this area, you can write, is pi r plus dr squared minus pi r squared, which is 2 pi r dr. So if you can do this integration numerically or analytically, you are going to get AM. Okay. Most of the time, this is not something you could do with your just directly. It will require numerical techniques or some kind of manipulation. So as much as possible, either I will suggest simplifications in the problem, or if I don't, you are supposed to come up with those simplifications. Like for example, you can take J naught of x and you can say I am considering the first 3 terms only. It's an assumption, it could still be inaccurate, but it is better than doing nothing. Okay, so what you need to do to integrate this, and I'll help as much as possible. And if it's a project, there is no excuse. You can't come and tell me I don't know how to integrate this. You have a computer, go write as a subroutine to do numerical integration. Okay. So that is AM. Typically this G of R, the problem can be simplified by typically giving it a 0. Say you depress your circular plate with your finger and you don't give it any initial velocity and let go. That's like saying G of R is 0 typically, which would mean BM is 0. So the entire solution would just be this. Okay. If I just ask you to think of the same geometry, same type of transport, except instead of wave equation, if we are thinking about the heat equation, what about this solution will change? And what won't change? What is the heat equation? It's almost the same thing except only the first derivative with respect to time, c squared partial u over partial r, second derivative, 1 over r partial u over partial r. So whatever you did related to w will not change at all. Right? The w part of the solution is still the same, but since you have only a first derivative, replace trigonometric function with a decaying exponent of minus lambda squared over t. That's it. Okay, so I'm not going to go through that separately. You should be able to make that bridge.
Is that lambda squared?
Lambda n squared, yep. Or lambda n or m, whatever you call your counting index. I would even summarize to say the exam is supposed to just test you how you apply boundary conditions to eliminate arbitrary constants. Whatever intermediate steps you need to give you this equation or hints to get there, I will provide it. Okay. So as practice, I would suggest working through problem set 12.10. That is where problems related to this topic are given. And if you see there, problem 4, problems 5 to 8, problem 12, those are all good. In fact, I think up to problem 22 is fine. You can try a combination of those. Up to problem 22. before we go, just one more question for you. Suppose you're not interested in the equation which involves r and theta, but you are interested in the other equation where you have, let's say, partial u over partial z, sorry, second derivative. How would that solution look like? Without having to do the entire work, can you look at this equation which has r and z dependence? Forget the time dependence also. Just look at this equation and tell me how will the solution look like. This is still the same. You would write your solution u is a function of w, which is a function of r, and some h, which is a function of z. So the w part, no change. Whatever we did so far will carry over. Look at this equation, tell me what kind of an equation you are going to get.
G double dot plus some constant square into, sorry.
Trigonometric or exponential, that is the choice. Trigonometric, because you are going to get something like h d squared h over dz squared plus lambda n squared or plus something times k squared times h equal to 0, which will give you a trigonometric solution. So you don't have to repeat the whole drill again, but if you are able to look at the equation and intuitively say, is this going to be a trigonometric or an exponential solution? That's how you move forward. You shouldn't be doing this derivation again and again for every problem. By looking, inspecting the equation, you should be able to say the general form of the solution should look like this. Now let me apply boundary conditions. Okay. So next lecture we'll do the spherical coordinates, and if time permits also the 2D Laplace equation, otherwise at the next lecture. Thank you.